You think you know what an oil tanker is. A big ship, carries oil. That's it. But here's the truth, and this is going to sound strange at first. Oil tankers are not primarily designed to carry oil. They are designed to make money. Every single inch of that ship, the shape of the hull, the number of tanks, the thickness of the walls, even the speed it travels, every single design decision is a financial calculation. And once you see it that way, you cannot unsee it. In the next 8 minutes, I'm going to show you how tanker design is actually a business decision disguised as engineering. Why tankers are so massive, why the walls are double, how owners make hundreds of thousands of dollars per day from a single voyage, and how one environmental disaster in 1989 permanently changed the shape of every tanker built since. Stay with me, because by the end of this video, you'll understand something that most people who work in shipping don't even think about. Let's start with the most obvious thing, the size. A VLCC, a very large crude carrier, is roughly 330 meters long. That's longer than 3 American football fields, end to end. It can hold 2 million barrels of crude oil in a single voyage. Now your first question might be, why so big? And the intuitive answer is, because it carries more oil. But that's backwards. Size is not about capacity. Size is about cost per barrel. Here's the key insight from maritime economics. The bigger the ship, the cheaper it is to move each barrel of oil. A ULCC, ultra-large crude carrier, is about twice the length of a coastal tanker, but it can carry roughly 8 times the cargo volume. Think about that. Double the ship, 8 times the payload. And transporting oil by tanker already costs only $5 to $8 per cubic meter. That adds just 2 to 4 cents to the cost of a gallon of fuel you put in your car. Larger ships push that number even lower. This logic drove shipbuilders to keep going bigger and bigger. In 1979, they built the Knock Nevis, also known as the Sea-Wise Giant. It was 458 meters long, 69 meters wide. It was so large, it couldn't even pass through the English Channel. It needed specially dredged channels just to dock. But here's where the business math gets more interesting. The Knock Nevis couldn't pass through the Strait of Malacca. That's a critical shipping lane between Malaysia and Indonesia. Taking a detour would add 3 extra days to a voyage. And 3 days, at the operating cost of a ULCC, could cost tens of millions of yen. So today, the sweet spot is the VLCC, the very large crude carrier. Big enough to get maximum economies of scale, small enough to access the most profitable shipping lanes. That's not an accident. That's a calculated business decision baked into every hull. Now let's talk about something that might seem like pure engineering, the double hull. Every modern tanker has 2 walls, an outer hull and an inner hull, with a space of a few meters between them. Why? The answer starts on March 24, 1989. The Exxon Valdez ran aground in Prince William Sound, Alaska. More than 11 million gallons of crude oil poured into the water. It became one of the worst environmental disasters in American history. In response, the U.S. Congress passed the Oil Pollution Act of 1990, OPA 90. It required all tankers operating in U.S. waters to have double hulls, and it forced the International Maritime Organization, the global shipping regulator, to follow suit with MARPOL Regulation 13F in 1992. By 2015, single-hull tankers were phased out globally. Now here's what's fascinating from a business perspective. Ship owners didn't just reluctantly follow the law. Many of them welcomed the double-hull requirement. Why? Because OPA 90 also introduced strict liability for oil spills. Owners were now financially responsible for the full cost of cleanup and damages. The Exxon Valdez cleanup alone reached $90,000 per ton of oil spilled in some estimates. A single major accident could bankrupt a company. The double hull creates a buffer zone between the ocean and the cargo tanks. If the outer hull gets breached in a collision or grounding, the inner hull protects the oil. Think of it like a thermos flask, 2 walls with space between them. It also serves another function. Those space between the hulls are used as ballast water tanks. filled with seawater when the ship is empty, to keep it stable and maintain the right draft in the water. So the double hull is simultaneously a safety feature, an environmental requirement, an insurance risk reducer, and a structural engineering solution. One design element, 4 business reasons for existing. Most people think the money in oil shipping is made while the ship is at sea. It isn't. The money is made and lost in port. Let me explain why. A typical VLCC voyage from the Persian Gulf to Japan takes about 45 to 50 days. The ship earns money for every single day it is in service. But when it's sitting in a port, loading or unloading, it's burning costs, not earning them. This is why tanker design is obsessed with loading and unloading speed. A modern VLCC has 17 separate cargo tanks. It doesn't just pump everything through one pipe. It has a carefully designed manifold system, multiple loading points, multiple pumps, so that crude oil flows in and out as fast as physically possible. There's also a stability advantage. When a ship carries liquid in a single massive tank, the oil can slosh violently in rough seas, a phenomenon known as free surface effect, which reduces stability and can amplify rolling. By dividing the cargo into multiple smaller tanks, that movement is contained, reducing internal wave formation and keeping the vessel far more stable in open ocean conditions. The multiple tanks also serve a cargo integrity function. There are approximately 300 types of crude oil in the world, different density, different sulfur content, different properties. Some cannot be mixed without damaging the refining process. So the ship can carry multiple types of crude simultaneously, each isolated in its own tank, maximizing the value of each voyage. Again, one design element, multiple business purposes.
Let's talk about fuel, because this is where owners either make or destroy their profits. A non-eco VLCC, an older, less efficient ship, burns roughly 70 tons of fuel per day when fully loaded, and about 61 tons per day when traveling empty. Bunker fuel, the heavy fuel that ships use, costs around $500 to $700 per ton. Do the maths on a round voyage, roughly 50 days, and fuel costs can reach $2 million to $3 million for a single trip. Fuel is the single largest variable cost in tanker operation. So how do owners manage it? One of the most important tools is called slow steaming, and it sounds almost too simple. You just go slower. One broker estimated that saving just 3 tons of bunker fuel per day on a 3-week voyage translates to more than $45,000 in cost reduction. Over a full round voyage, intelligent speed management can save $100,000 or more. This is why the hull shape of a modern tanker is obsessively optimized. The bulbous bow, that rounded protrusion below the waterline at the front, is specifically designed to reduce wave resistance at a ship's optimal cruising speed. A less resistant hull uses less fuel. Less fuel means more profit per voyage. So when you look at the shape of an oil tanker, you're not looking at engineering. You're looking at a fuel cost calculation that was done by accountants before a single piece of steel was cut. Now let's look at the actual economics of a voyage. Oil tankers operate in what's called the charter market. Owners either charter their ship to oil companies for a fixed daily rate, or they take spot market voyages, where they negotiate rate per voyage. On a normal day, a VLCC earns somewhere between $25,000 and $70,000 per day. During the 2025 peak season, rates soared past $125,000 per day on the Middle East to Asia route, the strongest in a decade. And when geopolitical shocks hit, like the Strait of Hormuz crisis in early 2026, rates exploded to $424,000 per day on some routes. One U.S. Gulf to China voyage was reportedly booked as a lump sum approaching $29 million. So how does an owner actually calculate profit on a voyage? They start with the freight rate, what the charterer pays. Then they subtract fuel costs, port costs, canal dues, crew wages, insurance, and their share of maintenance. What's left is the time charter equivalent, the TCE. That's the daily earning figure that everyone in shipping talks about. And every single design decision we've discussed today, the size, the double hull, the loading speed, the fuel efficiency, is ultimately aimed at maximizing that number. And remember, the ship isn't just earning the freight rate, It's carrying $120 million worth of crude oil in its tanks. A fully loaded VLCC at today's oil prices carries between $100 million and $200 million of cargo in a single voyage. The ship itself costs $150 million to $200 million to build. The cargo it carries is worth as much as the ship on every single trip. That changes how you think about every design decision. So let's come back to where we started. Is an oil tanker designed to carry oil? Technically, yes. But that's like saying a restaurant is designed to cook food. It's true, but it misses everything that actually matters. A restaurant is designed around profit per table, per hour, per ingredient. And an oil tanker is designed around profit per barrel, per voyage, per nautical mile. The size is about economies of scale. The double hull is about liability and insurance. The multiple tanks is about cargo flexibility. The hull shape is about fuel cost. The loading system is about time in port. Every rivet, every pipe, every curve of that steel hull, designed not just to carry oil, but to make money doing it. If this changed how you see something you thought you already understood, that's exactly what this channel is for. Drop a comment below. What surprised you most? Was it the scale? The double hull logic? The charter rates? If you want more videos like this, systems and industries explained through the lens of money and incentives, subscribe, because there's a lot more coming. I'll see you in the next one.